So, now we are starting the tutorial 4 with the assignment 1. Here we are provided with the signal EMG underscore doc2 dot dat. It is taken from a diaphragm of a dog. Crural diaphragm means it is near the leg. So, some fine wires electrodes, they are actually sewn in line with the muscle fiber 10 millimeter apart, and we get this signal. The 2 cycles of breathing is captured, and with very high frequency it is sampled 10 kilohertz. Okay. And we also to actually get that, to read that signal, we should look at that EMG underscore doc2 dot m. Now, our job is to write a MATLAB program for full wave rectification and or half wave rectification. In fact, we will do both, and after that we should apply that low pass Butterworth filter of order 8, and cutoff frequency should vary from 10 to 20 hertz, and we should actually analyze and evaluate the result of these 2 techniques of rectification and at least 2 different low pass frequencies. That means, the impact of choice of the rectification algorithm and the choice of the cutoff. Okay. And to compare the result, that the envelope is also given. The envelope is given here. Okay. That is also a signal hand drawn, that is given, that the what is the envelope signal here. So, first we take the EMG signal and that corresponding MATLAB files, that to read them, and we put the input signal and the MATLAB code in the same directory. Okay. The working directory of MATLAB, and our work starts from here. First we have to read the file. So, we load the signal, that then the variable EMG, we know the sampling frequency is 10 kilohertz. So, we are actually scaling that signal here, and we are finding out the length of the signal EMG, and with that we are finding out the time axis. Okay. That 1 to s length gives the ramp, and multiplication with 1 by fs, that is the that that interval that we multiply to get the exact time point. Okay. And then we normalize the signal, we eliminate the mean. Okay. In fact, these 2 order could be changed, we can remove the mean and then do this. Then we have loaded the that envelope also, what is given, which we need to compare, and again we have taken the corresponding that length, and using the figure and the subplot command, at the top we are showing the EMG signal and below the envelope. That means, what we are supposed to get. Okay. And here we are showing the EMG signal, and here is the envelope. We are supposed to get the envelope of the EMG signal like that, which should actually look like the envelope, the target envelope, which is provided with us. Okay. So, this is the target, this one is the target, this is not derived from the EMG. So, this part this is the for the reference it is given. So, first we do the high pass and the low pass filter. For the half wave rectification, first we do the rectification rather than filtering, that half wave and the full wave rectification. What we are doing? We are assigning the variable that EMG underscore H for that half wave rectification and EMG underscore F for that full wave rectification, that with the that we are assigning the length, and after that as the same as that the EMG signal, we are finding out the locations that where it is above the that 0. So, that gives us the that half wave rectification, and here what would be the value that we do not need. So, we have given here tilde, that we do not store that. For those locations, now what we are doing? We are assigning the value of the EMG signal. So, the positive half is restored, or we are actually preserving the positive half. The negative half, where the value is negative, it is because we have assigned it with 0, it has gone to 0. Now, in this case, the next for the full wave, we are finding out first where it is the value is greater than 0. Again we take that location and assign that in EMG underscore F, okay, here, and then we are finding out that the location again where it is negative, and please keep in mind that these location and this location would be different. So, first is it is assigning here the value of the EMG signal for the positive cycle, okay. And for the negative cycle, what it is doing? It is taking the negative of the value, that means it is making it positive and storing it at the same location. So, that the full wave rectification is happening because it is taking the positive half as positive, the negative half also it is making it positive and preserving it, okay. So, with that we get the full wave rectification, and here we see that output for the EMG signal given here. This is the half wave rectification and the full wave rectification. We can't actually see much difference from this plot, okay. Though there would be some difference, as we can get that operations are different, but it is not apparently visible from there the plot. So, we go for the next step, that is the low pass filtering. What is this purpose of this low pass filtering? Because that after the that rectification, what we will get, that we would get a that jagged signal, okay, or we can say a lot of ripple is there along with the DC signal. So, we would like to remove that the ripple or reduce the amount of ripple or the AC frequencies in that, and for that purpose a low pass filter is suggested with order 8 and first starting with cutoff frequency at 10. So, using the design criteria, that the order and the that 3 dB bandwidth, that we assign them N and FC, that 10, and Fs is we know that in this case that we have 10 kilohertz, that with that we have created the design, and then we have created the low pass Butterworth filter here using that criteria, and then first we actually use the that half wave rectified EMG signal to pass it through that Butterworth filter. And next we also get the filtered output of the full wave rectification using the same filter, we get it here. And now, we are having 3 plots, one below other. At the top, that we have that the half wave rectifier output, that which is that after filtering we are getting. So, second we are getting that low pass filtered full wave rectifier output, and at the below of these two we get the that envelope that is given as a reference. Okay. So, these three we expect here, and this is the 3 inputs that is given here. Okay. That at the top half wave rectifier output after filtering, that what we get, that because of the filtering lot of high frequency component has reduced. So, ripple has gone down, it does not look so jagged, it both of them they look close to the reference envelope. So, here we can see it more clearly. For the low pass filtering at 10 hertz cutoff frequency, the output of the half wave rectifier, it is shown with respect to the reference. Okay. Next, we change that cutoff frequency. Cutoff frequency is increased, that it has taken to 12.5. Now, as we are increasing the cutoff frequency, that the increase in that envelope, this part, it is following more with like the reference envelope. Okay. The movement is faster, but the ripple is increasing. Okay. So, that is the thing what we notice. Next, we increase it further, it has made to 15 hertz the cutoff frequency. So, more high frequencies are allowed. So, we get that this is the rise are becoming more actually smooth, and it is actually do not have much lag, it is following the same as that increase here, but ripples are increasing. Okay. So, with that let us move ahead, increase the cutoff frequency further. So, we are preserving up to 17.5 hertz, and we see that ripple has again increased a little more, and then we go for the 20 hertz, we get further increase. So, which actually makes it sure that the more we are increasing that cutoff frequency, the envelope is getting deteriorated. Okay. We cannot say that envelope is looking better, though it is actually changing faster and following that the faster change as with respect to the reference envelope. Now, let us put them together to study their effect side by side. Here we start with that we are starting with that the 10 hertz, and in each case the low pass filter order is same. So, only change is in the cutoff frequency, then going to 12.5, then 15, 17.5 and 20. What we see that as we are increasing the cutoff frequency, more and more ripples are coming in the output, and that when we compare with the reference signal, we find that is not a desirable one. So, out of them, though maybe the change may be little slower, that means the way it is increasing or decreasing, that may be better when we have more high frequency terms, but because of the presence of ripple in the output, we find that at 10 hertz the output was the best for that half wave rectifier. Now, we have to go for the full wave rectifier output. So, first we take that case that when 10 hertz is the cutoff frequency. So, we get some small amount of ripple at 10 hertz, then we move for that other cutoff frequency. Next point is 12.5 hertz. We are going for that. We see there is some increase in ripple. Next, we would increase it further to see that what is the change. So, it is increased to 15 hertz. Okay. So, as it is increasing, that it is the changes are coming in the same way. In fact, the sharp reduction it is followed here, but what we find that ripples are also increased. So, again it is increased further 17.5 hertz, and we see more and more ripples are coming. At 20 hertz, we see that the ripples are almost as big as the envelope. Okay. And to compare them, we put them together. What we see here, that starting from 10 hertz, as we increase the cutoff frequency to 12.5, 15, 17.5, 20, each of these case that we have increase in the ripple in the output, though at higher frequency the changes what is occurring in the reference envelope, those changes are reflected in a better way, but the amount of ripple that is getting in the output, that does not make it a good representation of the envelope. So, if we look at these cases, we can easily say that 10 hertz is better as a choice of cutoff frequency for that. And another thing we get, that when we are going for the full wave rectifier, the output is more closer to the reference waveform what is provided with us. Okay. So, these are the things we get. Now, let us conclude with the observations here. The envelope obtained from full wave rectified signal is smoother compared to the half wave rectified signal. Okay. That when we go for the full wave rectified signal, that it is would be smoother than the half wave rectified signal. The thing could be, we can look at the picture, one picture to make it easy, that let us take a sinusoid, okay, a sinusoidal signal. Now, if we have half wave rectification, what we will have? We will have the output would be like this, and after the filtering we will get this kind of signal. Compared to that what we will get in that, or let me clean this part, that, or I think better it would be, let me change the color. Okay. If we take full wave rectifier, we are getting one more, actually the negative parts are also having that. Now, if we look at the ripple frequency has increased. Now, because of that the rejection would be better. Okay. That actually giving rise to the fact that we are having a better actually signal as an output. Okay. So, we get a better signal as a output. So, smoother signal as a output. Second part is low pass filtered output with low cutoff frequency has smoother output as unwanted high frequency components are filtered out. When we are increasing the cutoff frequency, it is allowing more and more high frequency components and actually destroying the quality of the envelope. And in both the full wave rectifier signal and that what we get, and for the that half wave rectifier, that we found that low pass filter with cutoff frequency 10 hertz, it gives us the best output. Okay. So, that is our observation from this assignment. Thank you.